All right, welcome back. We'll keep talking about trigonometry and have one more glance at this beautiful unit circle and how it traces out the graph of the sine and cosine function as we track the value of the hypotenuse and the adjacent and keep track of whether we're in a negative or positive x direction or a negative and positive y direction. So I mentioned in the first video that one thing that we will do with these trig functions is that we will evaluate them at special angles. Here's the whole list of trig functions: sine, cos, and tan. Tan, by the way, can be defined not just in terms of opposite over adjacent, but also in terms of sine and cosine. Tan of x is equal to sine of x divided by cosine of x. And why is that the case? Well, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. If you divide those out, you get opposite over adjacent, which is tan. There's three more trig functions that are shown underneath. The first of the new batch is called secant, indicated by sec of x, and it's defined as 1 over the cosine of x. There's cosecant, which is 1 over the sine of x, and cotan, which is 1 over the tan of x. This is the full set of trig functions. The main angles of interest include these ones. I should add x equals pi to these. It really does belong in this core set of angles. So an angle of 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, and 180 degrees. These are the main ones that we work with. And then there's extended angles, like 5 pi over 4. 27 pi over 6, and so on. So angles larger than 2 pi indicate going around the unit circle more than once. There's also negative angles, where we go around the unit circle inside the clockwise direction. So the first batch of trig evaluations that we can understand in terms of SOHCAHTOA outside of these two special triangles are the sine of 0, pi over 2, pi, and 3 pi over 2. I'll explain why the sine of 0 is equal to 0 with a picture. So I'm going to draw a triangle that has a fairly large angle theta. That's the opposite. That's the adjacent. That's hypotenuse up here. Now what happens if we make that angle very small? What if we make that angle like 1 degree? What's going to happen? So I'm going to draw a 1 degree angle here. It's very hard to draw that angle. I've probably drawn a 5 degree angle or something, but it's supposed to be 1 degree. 90 degrees there. What's happened to the opposite is it got very, very small. The opposite shrunk down as that angle shrunk down. What's going to happen if we take that angle and scrunch it all the way down to 0? So I'll draw it best I can. So there's the adjacent side. And then I'm going to draw the hypotenuse. It's the same. Like I can't draw, like it's right on top. They're right on top of each other. Now what's the opposite of that? And how long is the opposite side if the hypotenuse and the adjacent are squished right on top of each other? And the answer is there is no opposite. The opposite's equal to 0. And sine is, so there's a 0 for the opposite. The adjacent is equal to the hypotenuse. And then sine is opposite, I'll put sine of 0 is equal to opposite over hypotenuse. Well, the opposite's 0. There's nothing. There's no length there. You got to really measure it like when they're squished right on top of each other. There's no side. Side length is 0. Divided by whatever the hypotenuse is. And it doesn't matter what the hypotenuse is. If the hypotenuse is 10, you got 0 divided by 10. If the hypotenuse is 5, you got 0 divided by 5. It doesn't matter what it is. It's just going to be 0. So that's why the sine of 0 is 0, just for that simple reason. What's the cos of 0 then? So cos of 0 is the adjacent over the hypotenuse. But look at what happens when the angle is 0. When the angle is 0, the adjacent and the hypotenuse are the same. They're scrunched right on top. There's no difference between them. If the hypotenuse is 5, the adjacent is 5. If the hypotenuse is 7, the adjacent is 7. So adjacent divided by hypotenuse in that case is just going to be 1. And then what's the tan? Tan of 0 is opposite over adjacent. So you got 0 for the opposite divided by who cares for the adjacent. I'll just say adjacent, which is equal to 0. So tan of 0 is 0, sine of 0 is 0, and cosine of 0 is 1. That's the basic reasoning. What about pi over 2? So for pi over 2, I'll draw a skinny triangle, but not so skinny that we can't see the angle. So there's the theta, here's the opposite, here's the adjacent. And what happens if we make that angle even closer to 90 degrees? So I'll do my best to make that happen. So here's the best I can do. Oh my God, there, okay. They're like kind of crossing the streams there. Oh man. Okay, so that's like 1 degree right there. Here's our adjacent. Here's our opposite, and here's our hypotenuse. So what's happening here is as theta goes to pi over 2, the opposite goes to the hypotenuse, and the adjacent goes to 0. The adjacent shrinks down to nothing. So any trig function that's defined in terms of adjacent divided by something is going to be 0 divided by whatever that is, which is going to be 0. And that's why the cosine, which is adjacent over hypotenuse, is equal to 0 at pi over 2. It's also why the tan function is undefined there. Tan is opposite over adjacent, so we would have whatever the opposite is divided by 0. The sine function, the sine of pi over 2 is equal to 1 because the opposite and hypotenuse are collapsing down onto each other. So you have 5 divided by 5, or 2 divided by 2, or 7 divided by 7, some number divided by itself. And then for the other angles that are here for pi, 3 pi over 2, we just have to do the same type of picture, but keeping track of whether the opposite and the adjacent are in the positive or the negative y, positive or negative x and y directions. Now, if we have this group memorized for these special angles, 0, pi over 2, pi, 3 pi over 2, just sine and cos, we can obtain tan at these four angles by using tan of x is equal to sine of x over cosine of x. So if we want tan of 0, it's sine of 0 over cosine of 0, which is 0 divided by 1, which is 0. Pi over 2, we try that and we get 1 over 0, which is undefined, as noted already. Now, what about other angles? So I had 3 of these in that very important list, and then there's some other ones in the list, the 60, the 30, and the 45. The way we get those is by memorizing 2 special triangles. The first special triangle is when the 2 non-right angles are the same. So the theta in the bottom left corner plus the theta in the top right corner are equal. So we have 2 theta is equal to 90, since the 3 sides must add to 180 degrees. So if 2 theta is equal to 90, that means theta is equal to 45. If those angles are the same, then the respective sides are the same. We'll keep it simple. We'll make each of those sides equal to a length of 1, since we're only interested in the ratio of the side lengths. Then Pythagorean theorem tells us that the opposite side has a length of the square root. So the hypotenuse squared is equal to one side squared plus the other side squared. So hypotenuse squared is equal to 1 squared plus 1 squared. So hypotenuse squared is equal to 2. Take the square root of both sides, and we get the hypotenuse is equal to root 2. Then, if we can construct this triangle, or know it from memory, then we can obtain what the sine and the cosine of pi over 4 are equal to, and the same for tan of pi over 4, just using SOHCAHTOA. Sine of pi over 4 is opposite 1 over hypotenuse root 2, so 1 over root 2. We get the same thing for cos, same thing for tan. Tan of pi over 4 is opposite over adjacent, so 1 over 1, which is 1. That gives us 45 degrees. The other two angles are 30 degrees and 60 degrees. So 30 degrees, pi over 6, is the smallest of those three sides. We'll set that length equal to 1. Since we only want the ratios of the side lengths, and 1 is the simplest number we can work with for ratios. I don't want to get into the geometry of it, but if we choose that side to have a length of 1, then the other side that's opposite from a non-right angle is going to be the square root of 3, and then Pythagorean theorem will tell us that the hypotenuse is 2. So we memorize this triangle as well, and then we can get sine, cos, and tan of pi over 3 and pi over 6, or 60 degrees and 30 degrees, using SOHCAHTOA. There's a useful trick for memorizing which side goes with which angle. So the pi over 3 contains a 3. So does the square root of 3. Pi over 6 is the smallest side. Across from it, so pi over 6 is the smallest angle. Across from it is the smallest side. And then Pythagorean theorem gives us the 2. So there's a way that you could construct it partially from memorizing a little bit, and then constructing the entire thing from that little bit of memorization. So just to give you an example of what you would do with these triangles, say you want sine of pi over 6. So you have to know which of these triangles to use. Pi over 6 is inside the 30, 60, 90 triangle, not the 45, 45 triangle. So you wouldn't use the one I've drawn to the top left, you'd use the one that's one to the right of that. We identify our reference angle for that problem, which is pi over 6. We're going to label the opposite and the adjacent with respect to that reference angle. So the 1 becomes the opposite, the root 3 becomes the adjacent. So sine being opposite over hypotenuse, we're going to have the opposite side to pi over 6, which is 1, and the hypotenuse, which is 2, and that's our sine of pi over 6, 1/2. Cosine pi over 6, so adjacent to the pi over 6 is a root 3, and then it's adjacent over hypotenuse for the cosine function, so root 3 over 2. And then tan of pi over 6 is opposite over adjacent, so 1 over root 3. Now, when we move to a different angle, we have to change our reference. So sine of pi over 3, I'm going to label that as a reference angle now. I'm going to circle it in red. Sine of pi over 3 is the opposite over the hypotenuse. So opposite pi over 3, not opposite pi over 6, opposite pi over 3 is root 3. And the hypotenuse is 2. So you have to keep track of what angle you're referencing and change the labels of which things are opposite, which things are adjacent accordingly. Now for the other two questions that are here on this slide, we have the pi over 4 triangle. So we got to move over here. And for this one, it doesn't matter which angle we use as a reference angle. They're both equivalent since they're the same. Sine of pi over 4 is 1 over, or opposite over hypotenuse, so 1 over root 2. And tan is opposite over adjacent, 1 over 1, which is 1. So the first step, figure out which triangle you need. Second step, figure out your reference angle. Third step, use your SOHCAHTOA. Let's look at some more complicated examples, including examples outside of the first quadrant. For sine of pi over 3, I'm going to write down that special triangle. So we have pi over 3, which is 60 degrees, pi over 6, which is not a reference angle. Across from pi over 6, our smallest side. Across from the pi over 3 is a root 3, And the Pythagorean theorem gives the other side as a 2. So hypotenuse squared is equal to 1 squared plus the square root of 3 squared. So hypotenuse squared is equal to 1 plus 3. So hypotenuse squared is equal to 4, which means hypotenuse is the square root of 4, which is 2. Okay, now our reference angle here is pi over 3. So we have opposite over hypotenuse with respect to the pi over 3 angle. So the opposite of the pi over 3 angle is root 3, and the hypotenuse is 2. Oh, I already had that one. Oh well. Okay, tan pi over 6. I don't have that one, do I? I do. I'll just draw it again. Tan pi over 6, so I'll draw out the triangle. Pi over 3. Pi over 6. 1, 2, root 3. And then select the reference angle. Our reference angle is pi over 6. So that's going to label our opposites and adjacents. This is tan is opposite over adjacent. The opposite from the reference angle is 1, and the adjacent is root 3. So 1 over root 3. Okay, extended angles. How do you do cos of 5 pi over 6? This is taught differently in different courses by different teachers. Sometimes there's trig identities that are used, like the cos and sine of a plus b formulas are popular to use for problems like this. You'd represent 5 pi over 6 as pi minus pi over 6, and then use a cos of a plus b formula for that. Another way is using the unit circle, and I'll do it that way, just so we don't have to dig into trig identities. This is a bit of a trick. It's a bit of a shortcut. We have to figure out where 5 pi over 6 is. We know that up here is pi over 2. There is 0. So we're comparing, we can hide the pi. We're comparing 5 over 6 to 1/2. So would you rather have 5 over 6 of $1 million or 1/2 of $1 million? 5 over 6 is definitely larger than 1/2. So we're past this. We're past that quadrant. We're past the A quadrant. We're somewhere at a higher angle than that. Now we can compare to pi. What's larger, 5 pi over 6 or pi? So cancel the pi's. What's larger, 5 over 6 or 1? Would you rather have 5/6 of $1 million or $1 million? $1 million is larger. 5 over 6 is less than a whole number. The number in the top is smaller than the number in the bottom, so you're going to get a number less than 1. That means we're not past pi. We're not past 180 degrees. We are somewhere inside the S quadrant. And here's the trick. Once we identify that we are inside the S quadrant, then the task is fairly easy. If the fraction is fully reduced, we can use the fact that we are in the S quadrant. In the S quadrant, the cosine function is negative. The fraction inside the bracket is fully reduced. So if it was, let's say, 15 over 6, that's not fully reduced. We'd have to take the 3 out from the top, the 3 out from the bottom, and cancel them. We get 5 pi over 2. But here we can't do any cancellations. It's fully reduced. And we can just get rid of the 5 that's in front. We can reduce it to a first quadrant angle. So again, this is a massive trick for dealing with extended angles. You figure out the quadrant that you're in. We're inside the S quadrant. Inside the S quadrant, the cosine function is negative. I'll write that down for anyone looking at the note later. Okay, and then we don't need the fact that it's an extended angle in the S quadrant anymore. We've built that into the minus sign we put in front. Now we just need to know what is the ratio of the side lengths of this triangle here, which is going to be equivalent to the first quadrant triangle. It's just moved over to that first quadrant. Just flip it over and find the ratios of the side lengths for that one. That's why the method works. We're just performing a flip and building in the fact that we're in the negative x direction, so the negative adjacent side. Okay, so we have minus the adjacent over the hypotenuse. So the adjacent for pi over 6 is root 3. I'm just recycling this get my laser pointer, just recycling this triangle up here. So the adjacent is root 3 and the hypotenuse is 2. So we have negative root 3 over 2. That's our answer. Now the one to the right, we're going to do the same type of trick. Where is 2 pi over 3? Where is 2/3? And it's negative. So how do we deal with negatives? We haven't dealt with those yet. So I'm going to draw a unit circle. I'm going to draw a 0. Negative angles mean we're going clockwise. So here is negative. Well, I got to draw a little bit better than that. Well, what's wrong? We can't draw it today. There. That's a little better. That's negative pi over 3. I want to do that again. I'm going to go another increment of pi over 3 units. So that'll take me here. Negative 2 pi over 3. Now what quadrant am I in? I'm in the t quadrant. And inside the t quadrant, the tan function is positive. So we've used the quadrant information, including the fact that we went into a negative angle. We're using that quadrant information to say that this is going to be plus the tan of just pi over 3. If we had moved up to, let's say, 4 pi over 3, that would have brought us into the s quadrant up here. And the tan function is negative there. We would have a negative tan of pi over 3. We're just taking the triangle that's in the bottom left, acknowledging what quadrant we're in and what that trig function is going to be in terms of positive or negative, because we're in the positive and or negative y and x directions. And then flipping it to the A quadrant, flipping it to the top right, and working with our nice special triangles that are there. This is the cheapest way to do it. Some might say it's even lame to do it this way. It's like cheating, because you don't have to think as much, but it works. Anyway, so tan of pi over 3. Now our reference angle is pi over 3. I'm going to go up to that triangle. So we have up here pi over 3. Tan is opposite over adjacent, so root 3 divided by 1, which is just root 3. As a reminder, we do have these other 3 trigonometric functions, secant, cosecant, and cotangent, and you can define them in terms of sine, cos, and tan, and obtain their evaluations that way, or you can treat them as their own standalone functions. Secant of x is 1 over the cosine of x, which is 1 over adjacent over hypotenuse, which is hypotenuse over adjacent. Cosecant of x is 1 over the sine of x, which is 1 over the opposite over the hypotenuse, which is hypotenuse over opposite. And then the cosine cotangent or cotan of x is 1 over the tan of x, which is 1 over opposite over adjacent, which is adjacent over opposite. So you could define these three trig functions in terms of those ratios as well, instead of going back to 1 over cos, 1 over sine, 1 over tan. You can kind of skip over that step and go directly to these identities if you want. It's up to you. So let's do these ones. Cosecant of pi over 4. So I'm going to say that's 1 over the sine of pi over 4. I'm going to use that method. That's my choice. I'm going to do sine of pi over 4. That's our 45-45 triangle. So, oh my god, it's not even a triangle. It's some type of weird shape. Okay, and then 1 root 2. Sine of pi over 4 is opposite of our hypotenuse. So we have 1 over root 2. 1 divided by 1 over root 2, which is just root 2. As a reminder, when you do division of fractions, if you have a over b divided by c over d, you can rewrite that as a over b multiplied by d over c. So as a more concrete example, 1 divided by 1 over root 2, you can rewrite that as 1 multiplied by root 2 over 1, which is just root 2. So that's the explanation for that step. It's just a fraction step that we use to simplify that double fraction. Okay, similar question, cotan at negative 5 pi over 3. So this is like the disaster one. This is the worst case scenario, the worst evaluation. You have an extended angle outside of the first quadrant. That angle is negative. Our trig function is one of the weird ones. It's not one of the nice sine, cos, and tan. So what do? Let's break it down into pieces. Let's first rewrite it as a nicer trig function. So it's 1 over the tan of that angle. Now we have to figure out what quadrant that angle is in. And then based on that, we'll have plus or minus. This is temporary. Don't write, if you're taking notes, don't write down the plus minus yet. Leave it blank. I'm just telling you it's going to be plus or minus the tan of pi over 3. We're going to figure out if it's a plus sign or if it's a minus sign entirely based on what quadrant that angle is in. Okay, so we have our pi over 3. We have a negative pi over 3 down here. We have 2 pi over 3. Negative 2 pi over 3 rather. We have a negative 3 pi over 3, or negative pi over here. Wait, yeah, I guess negative pi is over there. No, wait, I've confused myself massively. No, don't do that. It's all the way over there, never mind. Yeah. And then we have negative 4 pi over 3 up here. Oh, I'm gonna confuse things by doing it this way. I'll do it just by comparing fractions. Okay, so this is negative. We have to write down negative angles, so this is negative pi over 2. Negative pi. Negative 3 pi over 2. And this is negative 2 pi and 0. So this is labeling things going backwards, going clockwise. I want to compare 5 over 3 versus 1/2. So that's to compare 5 pi over 3 or 5 pi over 3 to pi over 2. 5/3 is larger than 1/2, so I'm past this. I'm past this negative pi over 2. Now I want to compare 5 over 3 versus 1. I want to compare 5 pi over 3 to pi. It's larger. 5 over 3 is larger than 1, so I'm past that as well. Now I want to check, is it larger than 3 over 2? 5 over 3 versus 3 over 2. That's a bit harder of a comparison to do. So let's make common denominators to compare them. I can multiply top and bottom of the first fraction by 2, so 10 over 6, versus multiply the top and bottom of the second fraction by 3, 9 over 6. It's larger, so we're past that one as well. Now we compare it to 2, 5 over 3 versus 2. Let's make common denominators. 5 over 3 versus multiply top and bottom of 2 over 1 by 3. We get 6 over 3. It's not larger than 6. 5 over 3 is smaller than 6 over 3. So we are inside the A quadrant. And inside the A quadrant, the tan function is positive. Then we can use our special triangle. Pi over 3, pi over 6, 1, 2, root 3. And then opposite over adjacent, so opposite's root 3, adjacent's 1. So we have one over root 3 divided by 1, which is 1 over root 3.